Wait, yeah,
not good.
just give it a bit of time.
So, because I think showing, I think the displacements are converged,
Yeah. Display the deviations.
deviations.
Yeah.
Deviation.
And that shows this communication, which
Yes.
I think is a publishable result.
Yeah. I think we need to be very careful if we then try to say that there's communication or there's response in the loop C.
Yes.
So we need to be and a reviewer will for sure come back to us and say, oh, but this is a region that fluctuates a lot. Are you
Yes.
sure that this is responding? And
Yes.
then-
Well, that's why I think it's good to have, come back and say, well, since we submitted it, we've done extra analysis
Mhm.
and we've tested this.
This is the initial structure of. Okay.
Initially, this morning, when we had a conversation with Jim, my suggestion was, if we have a model for gyrase B, a part of gyrase B, can we create a model, but a static model, is not to run simulations of the whole complex, or which are a bit of gyrase A, and see if the regions that the signal is propagating to actually are regions that at the interface with gyrase A, for example?
Yeah, well, that would be very interesting to know. So, in your, so it's probably easiest, can you show maybe the deviations, say, after 5 nanoseconds, just to see after deviations?
Yeah.
So, do you have it on the structure?
Structure.
So even this one, even are
Well,
these
that's
the
nice.
displacement vectors, or is this the deviations? I'm sorry. This one.
Displacement or
This one.
Okay.
Is the displacement vector. Because if that's the deviation, is this the deviation? No, this is the displacement.
Mhm.
So this is the displacement. What about the same, the errors for the deviation? That's what we also need to, yeah. So just like, yeah, that's fine. We can look at that one.
The error deviation of the
The dynamic, but that's fine. Just because that's also something we need to look. Imagine that you see a clear pathway going through all the way through here.
Yeah.
Because there's
That's-
like yellow.
That's how it looks, isn't it?
Yeah.
So it looks to me
Exactly. Yeah.
as though you have too many chairs in the way here.
So,
Chairs out of the way. Not necessary. Chairs piled up in
ooh,
appropriate. Okay. So you've got signal that where the yellow shows, you have signal going down here through the edge of this beta sheet,
Yeah.
then into these helices,
Yeah, exactly.
through
Yeah.
here, and then down here.
Yeah.
And so that's the pathway of communication,
Yeah. For what
which I think is really interesting. So it looks as though it's internal communication. So the beta-lactamase, it's external via loops. Here it seems to be internal.
And it's actually interesting because it uses a lot of secondary structure motifs,
Yes.
which is not very common either.
Yeah.
Most of the systems tend to use loops, but this one seems to have responses in very defined secondary structure elements. That's actually interesting.
And I suspect, so if I have to speculate, this is a machine. The other systems are, it's allosteric regulation.
Yeah.
Here you have to transmit a force.
Yeah, exactly. You need to save energy in because it's
So
a
it
way
does
to
it
have-
through more
Yeah.
rigid elements.
Yeah.
I think probably, and this is where you can't tell in 2 dimensions, probably these regions don't contact the gyrase A,
Yeah.
Yes, contact
They
with
do?
the-
but
What-
down here,
Yeah.
Is it this
So
region's
this region?
contact gyrase A? That's where a model of the thing would be very
I
useful.
have the
So-
model of the DNA carrier.
Yeah, but that's where having kind of our structure embedded
Yes,
into
yes.
the model and
Into the
having the same
model.
colors. For example, if you have Or,
Uh,
I think what probably a nice idea would be,
This is the ATPS domain, and this is the gyrate A, gyrate A, and for the transducer domain connect with the gyrate A.
yes, so what I would do, well, I don't know how easy this would be, but I would give it a try. Try to have a model kind of fitted into this structure of the whole
Would-
the whole complex.
So this is not in your model?
No.
No.
So this region's not there.
Yeah, and even eventually having gyrase B colored with deviations, and for example, gyrase A
Yeah.
in gray, so that we
Mm.
could see which regions contact.
So the transducer is yellow.
Yeah. Transducer.
This
Yeah.
this is a transducer.
I have a very hard time
This is
understanding where I
transducer.
fit.
But in contact with the gyrate A.
So on this here, which is this is the transducer.
But this structure is extremely open, but you can see the
Yeah,
In
because
the-
there's different.
in the difference in this paper. Yeah. Yeah. This is the yellow is the gyrate B and ATPS
Yes.
domain. This is the transducer domain connect with the this is
So we're actually simulating this one.
yeah.
Yeah, but
Right.
only the yellow
Mm.
bits.
The yellow
Yeah.
part.
Only the yellow
Okay.
bits.
Yeah. Only.
And then the transducer is at the far end.
Yeah, it should be here if we.
Here?
Yeah, I think it
Mhm.
should be there. Yes.
Okay.
Is that?
So
Yeah.
what you're showing is that the signal is transmitted to where the DNA would be.
DNA.
Does the transducer contact the DNA?
Yes.
Yeah.
Uh,
So it's
but-
so we are showing the appropriate communication.
Yeah, that's what. But is there any experimental structures? It doesn't need to be very detailed nor anything, or
Mm.
even for a different system, but for this state that we could use to try to create just a representative model of the complex. So that it doesn't even need to be for publication purposes, but for us to look at it and say this makes
understand,
sense.
yeah.
Exactly. Because this is a scheme, it's nice,
Mm.
but then if you want to look at the details, like which,
Or what
Yeah.
was that big complex you showed? Was that a cryo-EM structure?
For the structure.
It was in the PowerPoint, I think. Or
This is
the one with the yellow transducer.
okay. This is for the yellow
the
transmit.
yes.
Gyrate. Yeah.
But with the DNA, with the gyrase A and gyrase B.
No, only gyrate B.
Yeah. So you had the structure with A and B.
Yes, I have A and B. This is gyrate A and gyrate B.
Okay. And where's the transducer there?
Because even, we're not even
This is-
seeing,
Okay.
ATPS
But this
and
is
this transducer.
but
Right.
this is a different state, right? This is not the state we're simulating. This is the state, this is the open state in which the yellow bits are still really apart. There will be a point where they get together and form a dimer, right? Popan, correct me here if I'm wrong. Yes, it's not easy because
So-
it's really big conformational
Yeah.
changes.
So I think what's nice to know is which residues are most involved in the signal. So when you go from the ATPase site down to the transducer, which elements of the structure are involved? So how does the signal pass over time? And then, are those conserved residues? Is a good question to ask.
What about mutations like resistance?
Exactly, and whether.
Yeah.
So presumably, there are some of those are conserved because they are involved in the mechanical transmission of force. Others may differ between species, but it's just nice to know that that yellow signal is really interesting. So just to see how it lights up. So over a very short time, the signal will just go close to the ATP site, and then a little bit more time it goes further down, and then down to the transducer, which is really interesting to see.
Yes, I think I've already told you this, Bandit, but this type of plot is fine. I think it's for us is fine, but if you want to write a paper, this type of plot only makes sense if you have a scale going together with it, because well, we are familiar with the color scale. We use it quite often, but there's no reason for someone that has never used it before to know that red represents the regions that move more and dark blue is the regions that do not move. So this only all the DNMD figures where you have deviations mapped onto the structure, they only make sense together with the scale.
And I think the other thing here is that it would be interesting to see this picture excluding the C loop. Because the C loop is the largest deviation, so it means the scale is set by that.
Or you can even, if we're not certain that there's anything interesting happening there, we can simply even remove it from the figure. Saying that we didn't analyze it because.
Well, I think it's worth having a look to see what it shows. Do you have you had the figure with the structure at different times? It was in the same presentation, I think. So in your.
So this type of figure only makes sense with the scale. You can never
Yeah.
use
This
the
one?
scale.
Yes,
Yeah.
like this. Perfect. So that's 5 nanoseconds.
Yes.
That's 0.05. I see.
Yeah.
So you can see that the perturbation, it starts up there, and then this part keeps showing up, which is interesting. This part here. So I don't know what that is. It would be nice to know which residues that is. Then it comes down here, and it looks like these helices, are together transmitting the signal. So there's this one, they're packed on top of each other, aren't they? And then there's one behind as well. So
There should be the equivalent, because this is an homodimer, there should be exactly the equivalent on the opposite side.
So there are 4 of them?
Should be right. I
So
think
there's
at
4
least,
helices?
at least 3, and then 3 from the other dimer. I don't know if it's 4 or 3.
It looks like, so maybe I'm reading too much into it, I don't know the structure well enough, but this is like a focal point here, and so it's like the signal goes through the focal point and then spreads out across 4 helices, and then here the signal is quite large, so you can trace it all the way down. It goes through there.
And what the upper significant?
Yes, that's actually,
Yeah,
that's
so
actually
those
so interesting.
those I think are binding loops. So when they're not binding, they're released, so they go away. So I think they're involved in the catalysis, but they're not transmitting a signal. So I can understand why they move, because they're not binding anymore. So I don't think that their function is different. Their function is to be part of the active site, I think.
I was wondering, does that region interact with other proteins or known to interact with other proteins? Not that loop in particular. I was wondering about this bit here. Because they're not directly connected to this loop.
No, that's
So,
true.
and it's I was wondering whether there's anything interesting happening there. Well, sometimes it's not easy to know why they move. We know that they move, but yeah. It's not the biggest response, but it's still something. It's the same level of this bit here. So
Yeah.
But I think the whole scale here is being dominated by the C loops.
Yeah.
So if you just ignore those, then you find that the colours are much clearer for the other parts. And I think the C loop, it is interesting. It's very interesting if it is coupled, but it's the hardest thing to prove as well. Nice stuff. Yeah, I'd really like to know what's going on there. And it would also be very nice to know where any binding sites are in this protein.
Mm-hmm.
You know, we know things bind at the ATPA site,
yeah.
and as you know, maybe there are other binding sites.
Mm-hmm.
Yeah. So known mutation sites, the lead to resistance, or allosteric sites. Eventually, that will be interesting, and see if we can capture any of that.
In I'm just trying to see this avibactin structure.
A question that I forgot to ask you. So, what's the difference in the response between removing ATP, removing AMP, and removing the gamma phosphate? Do you see any like substantial difference in terms of regions responding?
But in the AM removing AMP PNP case, I think it's same
Is it the same regions?
the ATP, yes. Same regions.
Can you put the other?
But
Can you now jump into the ATP so that I can just quickly? Oh wait.
Yeah.
No, the plots. I'm sorry, I was looking at the plots. Yeah. But ATP, this is ATP.
Yes.
So there's this region here that seems like transducer, that peak over there, around 300, between 300 and 350, that looks bigger in the ATP. Could be just a question of scale. Just go back to the AMP.
AMP, okay.
No, probably not. AMP was the other one.
Yeah.
No, probably not. This could be just, but I think it's worth comparing them properly. Looking at the amplitude of the responses and see if there's something that behaves differently. If there's a region that has a substantially different behavior.
And
And the removal of gamma phosphate. Are you kind of?
this is remove of the gamma phosphate. Very big
Yeah, that's interesting because it seems like there's more asymmetries in the response. I'm not even considering the loop C, the C loop. Just even the transducer is quite different, the behavior.
It is, yeah.
And there's a lot of peaks there between 50, 100 and 150 that are way bigger than in the previous plots. In chain B, the peaks in between 50, 100 and 150, the residues kind of there, they're quite different between the monomers, but on chain B they're also higher than in the previous plots for ATP and AMP.
It's a little bit misleading because the scale is different on the left and
Oh
on the
yeah,
right.
it is.
Oh.
Oh, the
So
scale is
the
different.
scale is different.
Oh yeah.
So actually the response of the GHKL
even-
domain
It's probably the same,
quite
yeah.
similar.
Yeah, we need to be very careful. Yeah.
So the scale there is being dominated on the left-hand side by that very
Yeah.
large
Yeah. Well
C-terminal response in the transducer. Where is that? So the residue 420 or something? Where is that? That's
Oh, the big one. Oh, that's
Yeah.
the terminal. That's
And
the
where-
red bit here on in the end of the
that's
It's the
down here.
terminal. Yeah, I bet it's that one. Yeah,
Okay.
I don't, is
Oh,
that
this-
one? I bet it's this bit's over here.
And then there's some missing structure there.
Because we're not simulating the whole gyrase B.
Yes. So and that's where
I
it's
suspect-
truncated at the C terminal.
Yes,
Yeah.
is it truncated in, because I think we're only simulating the first 400 and something residues.
Right.
So the rest is still missing. So yeah,
I
I
think in
think
this case, because
yeah,
C N terminal connect with the C terminal of the transducer domain.
yeah,
so-
there's a big
This is big.
How many residues are we still missing in gyrase B?
Missing in gyrase.
We didn't simulate the whole protein, right? We only simulated part of it. Do you have any idea how big is the bit that we're missing? Roughly, you don't need to be exact number, so 100 residues for 300, whatever. Do you have any idea? No? It's fine. If you don't, it's fine. Yeah, it's fine if you don't. But I think, and the bit, just to be certain, the part that we're missing is in the C terminal. Yes.
Is that correct?
I'm asking, not-
C terminal about
The missing residues in gyrase B.
1, 4, 2, 6. This is
The missing residue.
of the C loop.
No. But besides this, is there any bits that we're still missing in gyrase B? We
I
did
think there are, because the structure you showed
was bigger
has this region underneath,
that we're not simulating.
which is not included. Do you have this other?
Missing in this part.
Yeah, I'm asking. Yeah, I'm not sure. I'm just asking.
If in this part I can check. This here and here missing.
It's missing.
Mhm.
Yeah, this is a terminal.
So,
then,
that,
yeah.
so there's some.
There's stuff then. Yeah,
It
because
would be so if we had the complete structure, it would be the signal would pass further down the transducer.
exactly would continue. Well, yeah, and to be honest, it's very weird for a protein to finish in the middle of a helix, and that's a
Yeah, no, it's clearly not into complete.
yeah, it's not. There's
structure.
something they're missing. Yes.
And
Sorry.
gyrase. How does the gyrase B communicate with gyrase A? It's through the C terminal region.
C terminal region.